Gnanam Paramam Dheyam. Knowledge is supreme.
Let us continue our discussion about the polynomials. We have seen in the last part that if you want to list all prime polynomials with real coefficients, then there are only two kinds. One is a linear one and the other is a polynomials which are degree 2 and their discriminant should be negative. These are the only two possibilities for a prime polynomial in real numbers. Now let us try to do this thing similarly for what about field Q? What about Qx? I want to find a possibility for two things. Number one, whether is there any given any degree n, given n, any natural number, I want to produce polynomial f with rational coefficients which is prime and the degree is n positive. So this will show that in contrast to the real numbers, here polynomials can be of arbitrary degree. There are prime polynomials of arbitrary degree. So first let us, this is what I want to show. So first let us consider the polynomial. Of course you can write down many polynomials of degree, linear ones of course exist. There are many linear polynomials which are prime and many quadratic also, degree 2 also, for example x square minus 2 or more generally x square minus p. They are all degree 2 polynomial. These are, as p varies in prime numbers, these are all degree 2 and they are prime polynomials over qx, in qx, prime in qx. Simply because we know what are the zeros of these polynomials in complex numbers. In zeros of this polynomial, for example v c x square minus p, this is square root of p with a plus sign or minus sign. These are the zeros. Minus p here, no, plus p is root p plus p, and square root can have two signs, either plus or minus. It is better to write that as small x, where x square is p, and these are these are non real, no, they could be real, they are non rational complex numbers. So therefore none of them is in VQ of this polynomial is empty set. So it doesn't have a linear factor. So therefore they are prime polynomials. Now at least one cubic polynomial, and just a method, and then I will write down a formal criterion. How do you test a rational polynomials are prime or not? So first let us look at the polynomial f equal to x cube plus 4x plus 2. This is a polynomial with rational coefficients. Actually they have this polynomial has integer coefficients, and I want to analyze whether f is reducible or not. So if f is reducible, the only possibility is it has linear, all the three linear factors, or one linear and one quadratic. These are the only two possibilities. So, only possibilities for f to be reducible are f is a product of linear, product of three linear factors, or product of a linear and a quadratic factor. Or in both the cases, the linear, as we have seen, linear factors correspond to the rational 0. So, in both the cases, one linear factor is there, or equivalently, f has a rational 0. Again, that means in our notation, V, Q, F is non-empty. That is equivalent to saying that f is irreducible. So, when can f be irreducible? A negation of that. So, f is irreducible if and only if V, Q, F is empty set. So, in other words, if degree of f is 3 and f is in Qx, then f is irreducible if and only if V, Q, F is empty set. So, to test whether the given polynomial x cube plus 4x plus 2, if I want to check it is irreducible, I should check whether this is empty set or not. And how do I check that? So, that is in general, it is easy to see that the only possibility for a 0 to be plus minus 1 and plus minus 2 are not zeros of this f. Note that plus 1, minus 1, plus 2, minus 2, they are not zeros of f in Q. Let us test that. That is, I just have to plug it in x equal to 1, then this is 1 plus 4 plus 2. So, a positive thing will not work clearly. If I put minus 1, this is minus 1, this is minus 4, that is minus 5 plus 2 is minus 3, is not 0. So, this we have checked. Similarly, this we check that plug it in, it do not give a 0. And how do I know that I only have to test this? That is because look at the constant term. The constant terms factors are plus 1, minus 1, plus 2, minus 2. So, in general, if somebody has a 0, that is speciality about Q, then these are the only two. This will become clear when I write more general statement soon. And the earlier statement that if I have a degree 3 polynomial over Q, then we know that it is irreducible if and only if this is at least one no 0 in Q. This statement is true for any field, because degree 3 polynomial, how can it factor over any field? That either one factor is linear and one factor is quadratic, or 3 linear factors. In any case, one linear factor occurs for arbitrary field. So, this statement is for arbitrary field. The only thing I use rational numbers here, that is enough to test that the divisors of the constant term with integers, integer divisors of the constant term should not be 0 of that f, then f will be irreducible over Q. Okay, so in general, you have realized that in general it is not easy to test even for Q whether the polynomial is irreducible or not. So now I am working, now we want to check whether we can give some better way to test rational polynomials are irreducible or not. So I am preparing for that now. For example, you start with the polynomial f in Q, and let us assume f is non-zero. Now this first thing you write this f as, take out a common denominator. See, f has rational coefficients, so each coefficient has a canonical representation, that is integer by integer. So from each coefficient I am going to make the common denominator by supplying up and down by in multiplying the. So I will write this as 1 by q f tilde, where this q is a non-zero integer and f tilde is actually has integer coefficients, because this is a 1 by q is a common denominator. So if I want to decide about reducibility or irreducibility of f in Qx, it's enough to decide for f tilde. So f is prime in Qx if and only if f tilde is prime in Qx. F tilde is prime in Zx. Because now f tilde is a polynomial with integer coefficients. So moreover, I will also assume that all the coefficients of f tilde, they may have some common factor. So we may also assume GCD of coefficients of f tilde is 1. Remember GCD, when we say GCD of integers, it's always a positive integer. So GCD of the coefficients, the GCD is also called the content sometimes, but I will not use it now until some time. So therefore, without loss, we want to find a criterion for integer polynomials to be irreducible, and for that I can also assume, it's not necessary, but I can also assume the polynomials are monic, but I will not do so. So page number 5. So this is a very important lemma. This lemma is important for this. So I have two polynomials g and f, g and h. So g is written as b0 plus b1x plus bmxm, and h is c0 plus c1x plus cn xn. These are two polynomials in Zx, and I want to call f, I want to call their product is f, g times h. So by definition f is reducible. G and h are proper factors if m and n are not, m and n are at least 1. Okay. So this product I have written it as a0 plus a1x plus sum a m plus n x power m plus n. So g is of degree m, h is of degree n, and then f is of degree m plus n. Okay, for a prime number, for P, prime number P, suppose that P divides these coefficients up to some place. P divides B0, P divides BR minus 1, and P doesn't divide the next one, BR, where R is in between 0 and M minus 1. Similarly for C's, that is P divides C0, P divides CS minus 1, and P doesn't divide CS. 0 less equal to S less equal to N minus 1. No? You start looking at the coefficients. The moment it doesn't divide, P doesn't divide that, stop there. Earlier all coefficients are divisible by P. Similarly here. Okay, then if that is the case, then what is the statement? Then P divides the coefficients, P divides A0 up to AR plus S minus 1, but P doesn't divide the next one, AR plus S. Let us prove this. This is very useful fact. See, P divides up to some place, P doesn't divide, P divides up to some place, P doesn't divide, then the same thing here happens. Okay, let us prove this and then we will deduce the consequences. Okay, so let us compute the coefficient. I want to write down a formula for Aj. So take any coefficient Aj. So for proof, if J is smaller than R plus S, then what is Aj? Aj is B0 Cj plus B1 Cj minus 1, it will go on Br minus 1, Cj minus R plus 1, and then I cannot go on to the, so the next one is Br Cj minus R plus so on plus Bj C0. I can go on up to, I can descend the index of C to 0. The index of C is descending and index of B is increasing. So this is Aj. So in this, P divides B0, P divides B1, P divides Br minus 1. So this sum is divisible by P. This sum P divides this sum. Similarly, now I don't look at B's, I look at C's. C0, P divides C0, P divides C1, P divides C of this one, because this one is J minus R is smaller than S. Because of this, J minus R is smaller than S. So therefore, this sum P divide this. So altogether P divide this. So that proves the first part. All these P divides all these guys. That is what we proved. So what we have proved is P divides A0 to AR plus S minus 1. Now I have to show that P doesn't divide the R plus the next one. So what is that coefficient? So you just write it again, R plus S. This will be again B0 Cj, and now it will go on till Br. What will be the coefficient of Br? That will be Cs, and plus b r plus 1 c s minus 1 and it descend. So this is b r plus s c0. See, this term is extra, and all these terms are divisible by p. This is also divisible by p. P divides, and this one p neither divides br nor p divides cs. So therefore, because p is prime, p doesn't divide br plus cs, br times cs, because since p is prime. Therefore, p cannot divide. That proves p doesn't divide ar plus s. That is what it proves the lemma. So remember this. I will immediately use it to prove some nice thing. So this is lemma of Gauss. Okay, what is it? We have polynomial f in Zx, integer coefficients. F is non-zero, and suppose, suppose f is of the form g times h with g and h non-constant polynomials with rational coefficients. G and H are rational coefficients and f is this. Then f has such a decomposition in Zx also. So that means, so in particular, if f is reducible in Qx, then it is reducible in Zx also. Okay, and proof, I will just say easy to verify. That will save me a couple of minutes. So for this is where you are using a very important property of the ring of integers, which says that the ring of integers has that fundamental theorem of arithmetic. That is, that in the modern language it is said that the ring of integers is a unique factorization domain. That means factorization exists, factorization into prime numbers exists, and it is unique, essentially unique up to order. So such a theorem is called fundamental theorem of arithmetic. So arithmetic we are calling it because we were the school days arithmetic was done with the integers only and rational numbers. Now as we go to college and when we start studying integral domain, then one calls them as a unique factorization domain. That means it's an integral domain where the corresponding property holds. And this fundamental theorem of arithmetic or prime decomposition of the polynomial kx, that is the corresponding theorem. So, so the continuing that, now I want to state a very important lemma which is used very, very often. That is called the to produce or to check a given polynomial in Qx is reducible or not, the following lemma is very, very useful, used very often. Lemma of Eisenstein. What does it say? it says that suppose I have polynomial f a0 plus a1x plus ak x power k. This is degree k polynomial in integers, and p be a prime number. So I should have said let this and p be a prime number such that p divides a0 up to p divides ak minus 1. The leading coefficient is ak, so p doesn't divide ak. P divides all other, but p doesn't divide the leading coefficient of f. And in addition to this, p square should not divide a0. Then f is prime polynomial in Qx. So before I prove this, proof is very easy. Before I prove this, I just have to say that immediate corollary is, if I take any x power n minus a prime number p prime, these polynomials are prime in Qx. Simply because the leading term is 1, so I can take this p, doesn't divide the leading term, leading coefficient, and the constant term is divisible by p, but not p square. Therefore, we can apply Eisenstein criterion and say that this polynomial is prime in Qx. Not only one prime, we can take two at a time, because then I can choose any, you can apply Eisenstein lemma to either p or q. We can choose, and nothing special about 2. We can go on till x power n minus p1 to pr. So, for example, x cube minus 6 or x power 8 minus 30. These polynomials are prime in Qx, because here I took 2 into 3 into 5. These are prime numbers. Here 2 into 3 and so on. So these will give lots of examples of prime polynomials in Qx. Now just let us finish the proof. So proof of that. Actually, okay. So the proof is essentially what we have done it in the earlier case, that if it factors, then write down the equations and then you will realize that you will get a contradiction, or you can also do it. So you write down and then check all coefficients are not divisible by p, and then again choose r and s like earlier lemma. So I would just say easy to write down the proof, easy to verify. Please do this. Now, just last couple of minutes, I will make some remarks about a finite field. So let me write this as an example. So let f be a finite field with q elements. We have not proved such a construction, but we will do it next time. We will do it sometime. So now I want to count the number of polynomials of degree 2 in fx which are not prime. in Fx. So how do I count that? Because it's degree 2, how can, and let us say number of monic polynomials. So how can a degree 2 monic polynomial will not be prime? The only possibility is it splits into two linear factors. Linear factors may be repeated or non-repeated. So that is only it can happen when x is of the f is of the type x minus some c times x minus d, where c and d are two elements in f, and you just have to count them, how many. So that means c and d varying in f, so we have to choose two elements. So they are how many? They are precisely, they can be repeated, so they are precisely q plus 1 c2. They are precisely so many polynomials because I am counting repeated also. So, and how many monic polynomials are there altogether? Altogether there are q square monic polynomials. Q square is the number of monic degree 2 polynomials in Fx. Because monic, so the degree x square coefficient is 1, and now you only have to count the coefficient of x and coefficient of constant term. So there are two positions. So and in field there are q elements, therefore we will have q square element. So how many will be prime among them? These are the non-primes, and the primes will be therefore the difference. So the difference, so what we know therefore is, therefore there are exactly q square minus q plus 1 choose 2. There are exactly so many prime polynomials, monic is included in our definition, prime polynomials in Kx Fx of degree 2. And what is this number? This number is nothing but q choose 2. So what did we check? We actually found out how many prime polynomials are there of degree 2 in Fx in a finite field with q elements. So in particular, K is not algebraically closed. Because if it were algebraically closed, then there will be only linear polynomials. But these are the number of polynomials which are prime polynomials, and this number is at least 1. So the only prime polynomial of degree 2 in Z mod 2x, it is x square plus x plus 1. Because q is 2 in that case, q choose 2 is 1. So this is the only prime polynomial. If I take Z mod p, then there will be more, and then you can list them. This information is very, very useful when you are applying these things to the practical use, like designing bank cards and ATM cards and pins and so on. So that we will deal it sometime in the when we deal with concrete applications. To summarize this lecture, in the last we have given examples of fields which are non-algebraically closed. That means there are polynomials which are not, they are polynomials which are not linear ones, and they are prime polynomials. And we have explicitly given examples of such polynomials over many fields like rational numbers, real numbers, and finite fields. Whereas the only field which we have stated to be algebraically closed is the field of complex numbers. and this theorem I will prove it in the coming lectures, and also give a general construction of an algebraic closure of a field. So this will also be in the coming lectures. Thank you very much. We will continue in the next time.